Welcome to this Bentley Systems training course on STAAD.Pro. In this video, we will learn how to define design parameters and perform code check on a steel structure utilizing the Australian standard for steel structures AS4100. This example has a steel-framed warehouse model having specifications, supports, and loadings already created and assigned. An analysis command has also been created already, so we are at a stage where we can begin defining our design parameters. To define our design parameters, we can click on the Design page and then go to Define Parameters while having AS4100 selected. This will open up a dialog from where we can add various design parameters to our model. Before we define any design parameters, let us understand some of the things that we need to consider while defining them. Details on all the design parameters related to the Australian Steel Code can be found under the Help section of STAAD.Pro. Here you can find out about the function of each design parameter and the default values that are taken by the program if you don't define them yourself. Many of these design parameters are common across different codes in the program and have similar functions, but some of these parameters will be code-specific, such as parameters available only to the Australian Steel Code. There are also some design parameters which can only be applied to physical members formed for the purpose of design according to AS4100. These are the load height position and the P-brace commands. All design parameters, except a few, can be applied to the physical members that you have created in your model by clicking on the Toggle Physical Member mode from the Geometry tab. Once you have toggled this mode, you will see the additional parameters related to physical members in your design parameters list, such as the P-brace command. Let us look into this P-brace command in a bit more detail. The P-brace command allows you to locate flange bracings along the physical member. Restraint types under P-brace that can be provided by the users and the description is depicted in this table as shown. Unless specified, physical member ends are assumed to be fully restrained. The order of restraint type with respect to increasing stiffness is shown in this table. While fully and rotationally restrained type is the most stiff and unrestrained type is the least stiff. The restraints provided by using P-brace command are checked to see if they are effective, that is, if they are placed on the critical flange as per section 5.5 of AS4100. The restraints that are not applied to the critical flange are considered to be ineffective, and hence are completely ignored. It should be noted that the critical flange can change for each load case considered. The types of restraints applied to the top and bottom flange at each location determines the effective section restraints, which is shown in this table. Based on the restraints that are determined to be effective, physical members are broken up into design segments and subsegments. Physical members are divided into segments by any effective restraint other than the lateral restraint. The segments thus created are then divided into subsegments by the lateral restraints. When performing the design on physical members, many design parameters are automatically calculated by STAAD.Pro as shown in this table. For example, moment modification factor as per section 5.6 of AS4100 is calculated automatically based on moment distribution for individual segments and subsegments. Calculation of some of these parameters also depend on how you have defined the P-brace command and the restraint types utilized within it. For example, the SKL parameter, that is the load height factor as per AS4100, is calculated based on the restraint types defined using P-brace and the LHT parameter, which is the load height position. The restraint types defined using P-brace and the resulting segment and subsegment layout also automatically determines the twist restraint factor and lateral rotation restraint factor as per AS4100. The SGR parameter, which corresponds to the nominal steel grade, is also automatically selected for each physical member based on the section types. You can also select the SGR parameter by yourself if required. Based on the SGR parameter, the tensile strength and yield stress are automatically calculated as per section 2.1.2 and 2.1.1 of AS4100. Getting back to the STAAD.Pro model, we need to first activate the physical member mode so that we can assign the design parameters to the physical members that already exist in this example. So I will close the design parameters dialog and toggle the physical member mode before coming back to the define parameters again. Let's add the nominal steel grade parameter first. If we don't assign this parameter to a member, then STAAD.Pro will select the steel grade based on the section type for that member. I will add steel grade 3 for this example. You will also notice that the parameter just added has a physical tag next to it. Next, let's come to the pbrace command. I will add this command to later assign it to my rafters and columns. The bracing locations need to be entered as a factor of the member length. I will enter the factors according to the position of my purlins and girts. Here I can choose the restraint type for the top flange and the bottom flange. The top flange being where the local y-axis of the member is pointing. For this model, I will provide the lateral restraints to the top flange and the bottom flange will remain unrestrained. After setting up the restraint, I will hit the Add button. Moving on, let's have a look at the Ly and Lz parameters. Ly and Lz are the length for general column flexural buckling about the local y-axis and the local z-axis, respectively. These are used in calculation of slenderness ratios. By default, these values are taken as the member length. If we have a look at the rafters, we will need to specify the value of Ly parameter as the spacing of our purlins. We will also have to provide Lz parameter for those rafters that are supported by the end posts. For all the other rafters, we can leave the Lz parameter undefined, so the default value of the member length for Lz will remain. Coming to the columns, we will need to specify Ly as the spacing of the girts, and we can leave the Lz parameter undefined. So I will define these parameters accordingly, which I will assign to the appropriate members later on. In this model, groups of members have been created already, so we can quickly select grouped members. I can do this by going to the Select tab and clicking on Groups. I will select the columns and go into the Selected Objects view by going to the View tab. So these are the members to which I intend to apply the steel grade parameter that I have defined. This model already has collinear analytical members of the columns and rafters grouped together into physical members, but we can see that we are currently only able to select the analytical members. To select the physical members, in order to apply the SGR parameter, I will go to the Select tab and click on the Members cursor. Now we can see that I am able to select the physical members, so I will select all the physical columns here and apply the SGR parameter to all of them. Similarly, I'm going to apply the pbrace commands for both the top and bottom flange to my columns as well as rafters. Next, I will apply the Ly parameter with value of 1.29 to the rafters and the Ly parameter with value of 1 to the columns. I will only apply the Lz parameter to the rafters that are supported by the end posts. I can now click on each design parameter to highlight the members where it has been assigned. In order to perform a code check based on the design parameters that we have defined, we will need to add a checkcode command. This command will check the adequacy of the members based on the specifications of the selected code, which in our case is the AS4100. I will add this command and then apply it to all the members other than the braces. After this, we are ready to perform the analysis. We can perform the analysis by clicking on Run Analysis from the Analysis and Design tab. Our analysis is now complete, and you can see there are some notes regarding our analysis. If we go into the output file, we can view these notes. And I can see there are some notes that STAAD.Pro has selected certain steel grades by default for some of the members. This is because we had defined the SGR parameter only for the columns. As for the rest of the members, STAAD.Pro has selected steel grades automatically based on the section types. Now let's go to the post processor, and within it, navigate to the utilization layout. This layout is where we can view the design ratio for the members to which the checkcode command had been added. All the members having a utilization ratio above 1 are failing members, and in the data area I can select the failed members tab to see the information on just the failed members. We can also quickly select the failed members by going into the select tab and filtering by property name of failed beams. In an isolated view of the failed beams that were selected, we can see that failures had occurred in our columns, rafters, and end posts. In this video, we worked with a few design parameters, including the pbrace command. When working on any structure in STAAD.Pro, you should check if the default values of the design parameters that you have not defined yourself are acceptable to you considering your structure. If not, you should make sure to define and apply them appropriately. This concludes our training video on defining design parameters and performing code check on a steel structure in STAAD.Pro utilizing the Australian standard for steel structures AS4100.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.